All right, so we're doing the Lhopital rule, which you guys have been looking forward to for a long time. So Jacob will be happy and so will everyone else. So we're going to determine limits of indeterminate forms. So limits where you get 0 in the denominator, or 0 over 0 as your answer, or infinity over infinity as your answer, to name a few. You can also use Lhopital rule to find any limit. It doesn't just have to be those, but you have to use Lhopital if you have indeterminate forms. So steps for finding a limit using Lhopital's rule. Step 1, check that f divided by g is an indeterminate form at c. So for example, the limit is as x approaches 0, you get a 0 in the denominator, or you get 0 over 0 when you find the limit, or theta, or infinity over infinity. So before, when we got that, we always had to factor or get rid of the stuff by multiplying so that we could actually fill in the value for c. But now we can use Lhopital's rule if it doesn't work. So step 1, check for that. Step 2, differentiate f and g separately. So you differentiate the top and then you differentiate the bottom separately, not like a product rule, but separately. And then step 3, you're going to find the limit as x approaches c of the derivative of f over the derivative of g. And then the limit is equal to the limit of c if you provide the limit as a number, or theta, or or infinity or negative infinity. If f prime over g prime is indeterminate form, so once again, if you get 0 over 0 or a 0 in the denominator or infinity over infinity, then you just have to find the derivative of those and go do it again until you can plug it in and not get that indeterminate form. So example 1, I'm using a basic one that we used in the past. So normally we have the example, limit as x approaches negative 3, x squared minus 1x minus 4 over x plus 3. Now normally you'd have to get rid of that x plus 3 because it's the problem, right? So normally we would be factoring, and we're back to my kindergarten writing because I'm doing this on my iPad. Normally we'd factor and then cancel off the x plus 3's, then we can fill in. But with Lhopital's rule, we don't actually have to do that. Okay? So I can just go equals to, oops, let me make this smaller. The limit as x approaches negative 3. Now Lhopital's rule says I just put the derivative on the top over the derivative of the bottom. So derivative of x squared is 2x. The derivative of minus 1x is minus 1. And negative 4 just goes away. Then I do the derivative of x plus 3 on the bottom. Not quotient rule, just the derivative of the top on the top, the derivative of the bottom on the bottom. So the derivative of x is 1, and then plus 3, there's nothing. Well, now if I plug negative 3 in, I'm not going to get an error. So I can now just plug it in. So I'm going to get 2 times negative 3 minus 1 all over 1, which I don't really need. And so I'm going to get 2 times negative 3, which is negative 6, minus 1, which is negative 7. Now if I use my other process where I factored it, I would get on the top x minus 4, x plus 1, oh goodness, over x plus 3, and I wouldn't be able to factor it anyway, so I'd be stuck. So now we can use Lhopital's rule to actually find every limit if we really wanted to. Okay? But we use it especially for the ones where we can't get it to go away, where we get that 0 over 0 or infinity over infinity. So example 1, determine the limit of the following. So the first one is the limit as x approaches 0. Well, if I plugged in a 0 right now, I would get 6 times 0, which is 0 in the denominator, and tan of 0 is 0. So I'd actually get 0 over 0, which is not good. But I do know that I can use Lhopital's rule to find it. So I'm going to go equals limit as x goes to 0. The derivative of tan x is secant squared x. And then the derivative of 6x is 6. Now if I plug 0 in, the denominator won't be 0, so I can plug it in. I'm going to get secant squared x is the same as going secant x, so secant of 0, and I plugged it in so the limit goes away, squared over 6. Now secant of 0 is just cos flipped. Well, cos at 0 is what x is at 0, which is 1. Secant is 1 flipped, which is 1. So I'm going to get 1 squared on the top over 6. So it's 1 over 6. And we're done. Okay. B, if I plug the limit as x approaches 0 into sine x minus x over x squared, sine x will be sine of 0, which is 0, minus 0 is 0 over 0 squared. So I get 0 over 0. So I have to use L'Hopital's rule. So I'm going to get the limit as x approaches 0. The derivative of sine x is cos x. The derivative of negative x is negative 1. The derivative of x squared on the bottom is 2x. So as you note here, I'm not doing quotient rule. I'm doing the derivative of the top by itself over the derivative of the bottom. Now if I plug it in, I'm going to get 2 times 0 on the bottom. So I'm going to get 0 in the denominator, which I still can't get. So what do I do then? I can't just plug in right now. I have to do another derivative of the top and the derivative of the bottom. And I keep doing that until I can plug in my limit without problems. So I rewrite my limit. The limit as x goes to 0. The derivative of cos x is negative sine x. The derivative of minus 1, it goes away. The derivative of 2x is 2. Now if I plug the 0 in, I won't get a problem in the denominator. I'm just going to erase this little dot. So now I can actually plug it in. That's 0. So I get negative sine of 0 over 2. Sine of 0 is what y is, that's 0 radians, which is 0. So I get negative 0 over 2. Can I get a 0 in the numerator? Yep, totally fine. I just can't get in the denominator. So my answer is 0. All right? C. So with C, I have the limit as x approaches infinity. E to the x graph looks like this. Right? So as I approach infinity on that graph, I'm actually approaching infinity of e to the x. So if I plugged in e to infinity, I would get infinity. Now, if I looked at the line y equals x, the line y equals x goes like this. So what would I be approaching as I was approaching infinity? Infinity. So if I filled this in right now, I get infinity over infinity, which I can't get. So what do I have to do? I have to do L'Hopital's rule till I don't get that infinity over infinity, or I don't get 0 over 0. So I'm going to do the limit as x approaches infinity. The derivative of x is 1. The derivative of e to the x is e to the x. Now that's actually the same as saying the limit as x approaches infinity of e to the negative x, right? Because I can just bring this up and raise it to a negative exponent. Well, the graph of e to the negative x is just e to the x reflected in the y-axis. So it's actually going to go like this. So as I'm approaching infinity of e to the x, I'm actually approaching 0. So my answer is just 0. So it's what it's approaching when you look at that infinity. And e to the negative x, as I approach positive infinity, actually approaches 0. So I don't have to do the derivative again. Okay. Then we go to D. Limit is x approaches infinity of ln x and x. If I plug those in, I'm going to get infinities again. So once again, I have to do L'Hopital's rule. So I'm going to get the limit as x approaches infinity. The derivative of ln x, remember when you take the derivative of a ln, you rewrite that value on the bottom, and then the derivative of that value beside the ln on the top. So I get 1 over x as derivative of x. And then on the bottom, I have the derivative of x, which is just 1. So the derivative of ln x is 1 over x in the numerator, and the derivative of x is 1. So I'm actually left with the limit as x approaches infinity of 1 over x. Now when I look at the graph of 1 over x, as I approach infinity, it looks like this. This is the graph of 1 over x. So as I approach positive infinity of the graph of 1 over x, I'm approaching 0 again. So my answer to this is 0. So it's knowing what those graphs look like as well. If not, you could plug in numbers that are going to get bigger and bigger and bigger. So if I did the 1 over x, and we'd learned this, as I approach infinity of 1 over x, it always equals 0. But you could plug in larger values and see what happens. So if I go 1 over 10, or I plug in a larger number, it would be 1 over 100, or 1 over 1,000. I'm just getting closer and closer to 0, right? So that's why my answer is 0. Okay. If I look at e, if I plug infinity in, I'm going to get infinity over infinity again, which is a problem. So I need to do L'Hopital's rule. And like I said, with any limit, you can actually do L'Hopital's rule. We just don't teach it at first so that you can learn the other rules too. So the derivative of e to the x is e to the x. So I have that on the top. The derivative of 1, or x, is 1. So now I get the limit as x approaches infinity of e to the x. When I look at the graph of e to the x, it does this. So I can't just have positive infinity over positive infinity or negative infinity over negative infinity, but my answer can be infinity. So as the limit as x approaches infinity of e to the x, I look over here as I'm approaching infinity, it's actually approaching positive infinity. So that's my answer. Last one.